You know, you see them everywhere, on just about every street corner, those silent workhorses of our entire electrical grid. But here's the thing about transformers. They aren't quite perfect. So today, we're going to dig into the hidden physics that explain exactly why these absolutely essential devices are constantly, quietly losing energy. Okay, let's start with something you've probably experienced. If you've ever walked past a big electrical substation, or even just a utility pole, you've heard it, right? That constant low-frequency hum? It's such a common sound that most of us just tune it out. But what if I told you that sound isn't just random noise?
That's right. That hum is actually caused by something called magnetostriction. It means the transformer's metal core is physically vibrating, literally expanding and contracting with every single cycle of the alternating current. And that sound you hear, well, that's the audible proof of energy just leaking away into the air.
Now, what's just wild is how incredibly good transformers are at their job. I mean, they often operate at over 99% efficiency. That makes them one of the most efficient machines humans have ever built. Which, of course, raises a really interesting question. And that's the mystery we're here to solve. That final 1% might not sound like a lot, but when you think about the millions of transformers running 24/7 all over the world, it adds up to a massive amount of wasted energy. We're talking enough to power entire cities. So let's play detective and track down where it's all going. So, our investigation starts by splitting the problem in two. It turns out that pretty much all transformer losses can be sorted into two main buckets. The ones that are always there no matter what, and the ones that change based on how hard the transformer is actually working. Think of it like this. On one side, you have core loss. This is kind of like the standby power on your TV. It's happening as long as a transformer is energized, even if it's not actually powering anything. But on the other side, you've got winding loss. This is more like the gas your car uses. The faster you go and the heavier the load, the more fuel you're going to burn.
Okay, so let's start with our first culprit, those constant, always-on losses. For this, we have to go deep inside the magnetic heart of the transformer, the iron core itself, to find the source of this persistent energy drain.
The first type of core loss is called hysteresis loss. Just imagine the core is made of billions and billions of tiny, microscopic magnets. The alternating current forces all of them to flip back and forth, changing their polarity 50 or 60 times every single second. All that frantic flipping creates a kind of internal friction, and that generates heat. And that heat, that's wasted energy.
The second core loss comes from something called eddy currents. Now, because the iron core is a conductor and it's sitting inside a powerful, constantly changing magnetic field, tiny little circular currents get created inside the core material. You can picture them as little electrical whirlpools that just spin around, going nowhere and doing nothing useful except, you guessed it, generating even more heat.
All right, we've cracked the case on the constant losses. Now, let's turn our attention to the other side of the equation, the variable losses. These are the ones that happen in the copper windings that are wrapped around that core.
This is the biggest variable loss, and it's usually called copper loss. It's really just simple physics. Every wire has some amount of electrical resistance. So as current flows through those copper windings to power our homes and businesses, that resistance basically creates friction for the electrons, and that generates heat. The more current that flows, the more heat you get.
But here's the crucial part. This relationship is not a straight line. The loss actually increases with the square of the current. What that means is, if you double the load on a transformer, you don't just get double the copper loss, you actually get 4 times the loss. This is a massive deal for the engineers who are designing our power grids.
And all of this leads to this really beautiful, elegant principle in transformer design. A transformer is running at its absolute most efficient when the constant core losses are perfectly balanced by the variable copper losses. It's this perfect sweet spot where the total combined losses are as low as they can be and the transformer is just humming along at peak performance.
So let's just recap our whole investigation with this table. You can see it all laid out here. Core loss on the left is constant, and it happens in the iron core. Winding loss on the right is variable and happens in the copper windings. And notice this. Core loss depends on voltage, but the winding loss depends entirely on the current being drawn. Engineers even have specific tests, like the open circuit test and short circuit test, to measure each of these precisely. So, now that we've identified the culprits, the big question is, how do we fight back? This is where some really clever engineering and materials science come into play to try and minimize these inevitable energy losses. So, to cut down on that hysteresis loss, engineers use a really special material called CRGO silicon steel.
Its grain structure is designed to make it much easier for those tiny internal magnets to flip back and forth. And to stop those pesky eddy currents? Well, the core isn't one solid block of metal. It's actually built from hundreds of ultra-thin steel sheets, each one insulated from the next, which breaks up the path for those electrical whirlpools. Now, the solutions for copper loss are a little more straightforward. To lower the electrical resistance, you can either use thicker wire, which is kind of like using a wider pipe to let more water flow through, or you can use materials that are even better conductors than standard copper to begin with. And this is why all of this really, truly matters. Chasing after these tiny percentage points in efficiency isn't just some academic exercise. A single percentage point improvement, when you apply it across the millions of transformers that make up our global electrical grid, translates into saving terawatts of power. That's literally the equivalent of taking entire power plants offline for good.
So we're left with this final thought. Through incredible engineering, we've pushed efficiency to 99% by basically battling the fundamental laws of physics. But can we ever achieve perfection? Could some breakthrough in material science finally eliminate that last 1% and lead to a 100% efficient, truly perfect transformer? Well, the quest for that perfect machine continues.